Hi everyone, welcome back to another video. I would like to start off by saying please do not mind all the construction sounds going on. I'm not sure why there's a lot of construction going on over here this early in the morning. No, I'm just kidding. But yeah, please don't mind all the noise. It shouldn't be too loud. Hopefully I speak a lot louder than the construction. But anyways, today I'm at this beautiful residence here around the Palm Desert area. It's very hot. It's sort of the middle of summer. Or you know, it's summertime. And it's very hot. It gets up to around 115 to 120 degrees out here, so it's very hot. But I'm in the shade right now, so we should be fine for maybe the next 5 minutes. I'm just kidding. But anyways, that has nothing to do with this video. So on my channel, I like to talk a lot about the biology of, well, specifically plants. You know, we talk a lot about the concepts of these biological processes and whatnot, and different pathways and all that. But I really want to also talk about chemistry. I really like the sciences. And well, what's biology without chemistry? I feel like there's no effective way to learn biology without having a basic understanding of chemistry first. So today's video is going to be very chemistry heavy. I never really talk about very complex concepts on this channel, mainly because I would like it to be friendly to all different types of audiences. So yeah, it's not going to be obviously something that's impossible to understand, like quantum mechanics. But yeah, just a little heads up, today's video will be very chemistry heavy. So I feel like you're all curious to know what today's video is about, and today's video is going to be a bit basic, to be honest. We're still going to tie back this chemistry to biology. So today's video is going to be all about carbon. So carbon is a single element. So yeah, that's what today's video is going to be focusing on, the element carbon. So to start off, carbon is a non-metal. So on the periodic table, the elements are differentiated into different categories based on properties. So we have elements that are metals, elements that are metalloids, we have non-metals, and then well, breaking them down, we also have like transition metals and lanthanides, actinides, all different kinds of elements. But yeah, those are the three main groups: metals, metalloids, or semi-metals, I believe is another name for them or term, and non-metals. So carbon is a non-metal. We know this because in its solid state, carbon is not shiny like most metals. It's not, we cannot shape it, or it's very hard to shape it at least. So it's not ductile or malleable, meaning it can't be pressed into like a sheet, for example, like those metal sheets we see, or it cannot be shaped into like a wire. So yeah, we cannot shape it. And then something else about carbon is that it's not really good at conducting electricity. Probably not at all. But I'm not too sure. I'm not a physicist, so but yeah. It's not good at conducting electricity. So these are all properties or characteristics of non-metals, and well, carbon definitely is not a metal. So yeah, so something very interesting about carbon, what inorganic molecules, which are molecules that contain carbon and hydrogen, more specifically carbon and hydrogen bonded together. So yeah, just wanted to point that out. So something very cool about carbon is that it's able to form these very long chains. So when we look at the macromolecules important to life, most of them will have a foundation of a hydrocarbon chain. And sometimes these hydrocarbon chains are very long. Hydrocarbon just meaning that we have carbon and hydrogen bonded to each other. Okay, so many atoms, but only made up of two different elements. Okay, so something cool about carbon as well. I swear, I always say that it's cool because it is, you know. So carbon has 4 valence electrons. So valence electrons, I hope that sounds familiar to you all. Maybe you're recalling that term from your high school chemistry class. Valence electrons, meaning that, so electrons, I'm pretty sure you all know what electrons are, but just to, you know, touch base, electrons are subatomic particles that are negatively charged. So the subatomic particles of an atom are the neutrons, protons, electrons. They all have different charges except for neutrons. Neutrons do not carry any charge. But yeah, carbon has 4 valence electrons. These electrons of the atoms live, or live, I guess, or take up different shells. So the valence shell is the outermost shell, and the valence electrons are the electrons that live in this outermost shell. So valence electrons are very important to understand in chemistry, because valence electrons will be the reason for these molecules or atoms or compounds to react. So electrons, I would say, drive reactions. So yeah, carbon has 4 valence electrons. Most atoms are actually looking to fill up their valence shell with 8 electrons. So except for like hydrogen and helium, those are the smallest atoms. Hydrogen at most can have 2 electrons in its valence shell. Well, hydrogen and helium only have 1 shell. So the most electrons they can carry is 2 electrons. But other elements can carry 8 electrons in their valence shells. Okay. So something else about carbon is that it will most likely form covalent bonds instead of ionic bonds. So ionic bonds are bonds formed between metals and nonmetals, whereas covalent bonds are bonds formed by 2 nonmetals. So these are differentiated because ionic bonds involve a transfer of electrons. So like one atom is giving up all of its electrons to another atom, saying, here you go, take all my valence electrons so that my outermost shell can be full. And covalent bonds will involve a sharing of electrons. So an atom has 4 valence electrons and another atom has another 4. So they're gonna be like, hey, do you want to share so that we can both be happy? So yeah, that's my very like kid-friendly explanation of these different types of bonds. But yeah, the reason behind carbon wanting to form covalent bonds instead of ionic bonds is because it's a lot more favorable energy wise. So it's a lot easier for a carbon atom to share 4 electrons with another atom or another 2 atoms, because, well, in order for a single carbon atom to reach its full octet or 8 valence electrons in its outermost shell, it needs to bond with at least 2 other atoms. So an example of this is CO2 or carbon dioxide. So a single carbon atom is bonded to 2 oxygen atoms, and you know they're all pretty much happy. Well, except, well, the oxygen has 2, but no, in this case the carbon is happy. Okay, it's satisfied, it has its 8 electrons and it's done for that time. So yeah, basically carbon will form covalent bonds because it's a lot more favorable energetically. It's a lot easier to share electrons than to just transfer, especially when you're transferring more than, I would say, 2-3 electrons, because yeah, it's just more work for the atom. And you know, a lot of the times nature it's very interesting. Nature seems to be pretty lazy. As complex as nature is, it usually tends to pick the pathway that is easiest or most favorable. Because, you know, energy, organisms like to conserve energy. Wasting energy is just not a good idea. But yeah, so that's a little brief introduction of the chemistry of the carbon atom. Okay, so so all living organisms have carbon or are made up of carbon and hydrogen, because all organic molecules contain both carbon and hydrogen, like I said, bonded together. You know, the definitions are kind of confusing because I've heard sometimes that carbon alone in a molecule makes that molecule organic, and I've heard others say that no, like carbon must be bonded to hydrogen in a molecule for it to be considered organic. But yeah, I'll just stick to that definition, okay? The hydrocarbon and all that, where they must be bonded together. Because, well, like the simplest organic molecule is CH4 or methane. There's a smaller molecule, CH3. I forget the name of CH3. But the reason this is not considered the smallest organic molecule is because it's not really stable. So CH3, in CH3, carbon is not satisfied. It needs I believe 2 more valence electrons to be satisfied. So although CH3 can exist on its own, it's very short-lived since it's highly reactive and is looking for someone else to get 2 electrons from, or something else, another atom I should say. So yeah, I'm just going off my notes, so if I take brief pauses, I'm just looking because I want to mention everything I wrote down. So carbon is present all throughout Earth, which is very cool. Carbon is present in the atmosphere, in the form of carbon dioxide, CO2. And it's even present all the way down in the depths of the ocean, found in its inorganic form. Okay, so carbon spreads through the carbon cycle, so it's transferred through the carbon cycle. This is a long process, but it's not long, but you know, all these processes are pretty complex in their own ways. But basically, plants take in carbon dioxide from the atmosphere because they need carbon and oxygen for their metabolism. Okay, so organisms will eat these plants like herbivores. So let's take, for example, a cow. So cows are herbivores. They graze all day and eat grass, which is a photosynthesizer. So grass will take in carbon dioxide. The cows will eat this grass, which the carbon will then transfer to the cows, and then predators, including us humans, will eat these cows and then get part of that carbon as well. So it's all just a big transfer and recycling of carbon. Okay, so yeah, organic molecules will not, like I said earlier, organic molecules usually have hydrocarbons as their foundation. So carbon and hydrogen will also bond with other important elements to life, ones like oxygen, nitrogen, sulfur and phosphorus. Okay, so I like to remember this as chomps, CHONPS, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are all elements that are extremely important to life. Okay, so since we're talking about carbon and all of its distinct features and behaviors and characteristics and all that, I feel like it's important to also talk about what are known as isomers. Okay, so isomers have a lot to do with the molecular shape of a compound. Okay, so isomers are differences in the architecture or variation in the architecture of these compounds, okay? So there are three different kinds, to be specific. One of the types of isomers are structural isomers. So these are differences in the shape of the molecule, okay? So let's take, for example, the molecule C5H12. I don't know the name for this molecule, but when we look at the shape, we can see different ones. One shape that we see, I'll try to add pictures from online, but I'm just gonna try to explain it first. So C5H12, we can see a line of carbon atoms lined up, bonded to each other, single bonds, and then hydrogen atoms branching off of each carbon atom. I'll try to add a picture. Hopefully I'm explaining it decently. And another variation we could see of this same chemical formula is a shorter chain of carbons, one carbon being bonded to three carbons and one hydrogen, and then the other hydrogens branching off. So this is an important difference, because in biology or in living organisms, structure directly relates to function. So since these are the same molecules, they have the same atoms and same elements, but since their shape is different, they will end up having different functions, okay? So very cool. Another type of isomer is what's known as the cis or trans isomers. Cis and trans isomers are the differences in arrangement about a double bond of carbon. So usually when we see double bonds in a molecule, it's not flexible because this bond can break. Usually single bonds are a lot more flexible, but double bonds and triple bonds will not be as flexible and will break. So these cis and trans isomers, cis means that the molecule has two similar groups on the same side. I'll add pictures again. And then a trans isomer will have similar groups on opposite sides. So I'll add a picture just so you can know. But yeah, they're like the same type of molecule, but just on different sides, okay? And lastly, we have enantiomers. So the definition for enantiomers is differences in spatial arrangement around an asymmetric carbon. Oh, wow, what a handful. But basically, enantiomers are mirror images of each other. I'll add a picture as well. Mirror images of the same molecule. So so for example, let's take a left shoe and a right shoe. Shoes have the same function. Well, left shoes and right shoes have the same function, you know, for walking, for style, whatever you use shoes for. But we cannot use them the same way necessarily. So we cannot put on a left shoe on a right foot. You know, it just won't work out. So enantiomers are the same, I would say. They work this same way as the analogy or example. Okay, so let's just think of enantiomers like the left shoe and right shoe, mirror images of each other, okay? So lastly, let's also talk about the functional groups. So carbon and hydrogen, you know, like I said, they form the base of these biological molecules, but they can't do all the work. So this is when we're going to have functional groups come into play. So the functional groups are these chemical groups with their own unique properties or shapes or even charges that allow them to react in specific ways. So they're very handy and very useful. So a few examples. I don't know all the functional groups, so I'm just going to briefly mention it. A few examples will be a hydroxyl group, the chemical formula being OH, so an oxygen and hydrogen atom bonded together. Hydroxyl group, okay, and a phosphate group, the chemical formula being PO4 2-. So 2- because it has a -2 charge. This just has to do with the electrons and protons and all that, okay? So yeah, those are two examples of functional groups. Functional groups are extremely important to these biological molecules. Like I said, they're going to react in different ways, so they'll have different results, different products, okay? Now finally, to finish off this video, this has been one of my favorite videos, to be honest. I love going over chemistry. Chemistry likes to focus on the very fine details. And you know, it's important to focus on these fine details in order to understand the big picture, okay? So yeah, very fun. But anyways, the last thing I want to talk about is a specific example, okay? So let's talk about ATP, or adenosine triphosphate. Adenosine triphosphate is also known as the energy molecule, but I wanted to mention it because I find it very interesting and very cool, okay? So adenosine is an organic compound, you know, a long chain of hydrocarbons with other functional groups. One of these, this compound adenosine is attached to a group of 3 phosphate groups, okay? So like triphosphate, 3 phosphates groups, okay? So adenosine triphosphate actually holds energy in these phosphate groups. So when adenosine triphosphate reacts with water, it becomes adenosine diphosphate, okay? This is because one of the phosphate groups break off of adenosine triphosphate and react with the water. So we see this reaction taking place in living organisms, okay? So it will react with water, and this is what's known as a decomposition reaction, because we have one compound, adenosine triphosphate, breaking down into 2 or more things. So adenosine triphosphate breaks off a phosphate group, becomes adenosine diphosphate, okay? More specifically, this is also known as a hydrolysis reaction, because water is doing the breaking down of the compound, okay? So hydro referring to water, and lysis referring to breaking apart or like breaking down. So this is a hydrolysis reaction. So all compounds hold chemical energy, but adenosine triphosphate also holds potential energy being held within these bonds, okay? So yeah, I really hope you guys enjoyed this video. I had a lot of fun talking about the chemistry of life, you know, the basis of life, carbon. The carbon forms the backbone of all life, so very interesting. But yeah, thank you guys for watching. I hope you learned something. Have a nice day. Thank you.